Hi, I'm Pradeep Ramani and I'm an architect at NVIDIA. Co-presenting with me today is Chris Cheka, research scientist and founder of the CUDA project. We are here today to talk about how to optimally program Hopper Tensor cores for powering applications like deep learning and high-performance computing using Cutlass. Cutlass is a CUDA C++ template library which provides extensible software components which are designed with a two-pronged approach. Firstly, to make maximal use of the architectural feature set of NVIDIA GPUs, and secondly, to provide abstractions for optimally structuring matrix computations like GEMS, convolutions, and BLAST tree. This is achieved by implementing a software hierarchy which expresses different levels of the CUDA execution model and at each level structuring appropriate software components for composability and reuse. Namely, we start off at the device level at the top, which is host facing and implements algorithms like GEMS, convolutions, and BLAST, which is composed of the kernel level, collective level, which in turn uses the atoms, which is composed of finally the architecture intrinsics. We will revisit this hierarchy later. Cutlass can be found on the NVIDIA GitHub page in NVIDIA/Cutlass, with the latest revision being 3.0. There have been numerous prior GTC talks all the way back from 2018, which cover different aspects of Cutlass as well. References to them have been linked here for convenience. As can be seen, Cutlass 3 provides near optimal performance on a variety of kernel classes, data types, and layouts compared to our de facto linear algebra library, cuBLAS. Beyond this, developers can also extend and tailor Cutlass for their specific use cases to see even more performance gains. While Cutlass does not provide the heuristics or the stability guarantees like cuBLAS, we have strived to empower developers through the availability of the Cutlass profiler and have also maintained a relatively stable device-level API over the years. Moving on, Cutlass team is excited to present to you our roadmap for this year. We plan to primarily execute focusing on the 3.x code path while continuing to provide critical updates for the 2.x code path. Along those lines, we have a rich feature set coming up for this year, including convolutions, epilogue visitors, fusions, stream-K, reduced precision FMHA kernels, and many more. We'd love to hear your feedback via GitHub on features you'd like to see added to Cutlass 3 and how best we can align to help you. The higher order agenda for today would be to cover some of the interesting architectural features of Hopper which are applicable to Cutlass, and then moving on to a detailed tutorial on the Qt metaprogramming model and how it acts as the backend of Cutlass. Then we'll see a tour of Cutlass 3 APIs, its layered architecture, and ingredients for building a high-performance GEM computation using the 3.0 API and for targeting the 4th generation Hopper Tensor cores. We'll wind up with a tour of the new Python Cutlass API, which we plan to introduce in Cutlass 3.1. At this time, I'd like to thank and acknowledge the active support and adoption of Cutlass from the GitHub community. Our community has grown over 10x in just the last 1 year, and it has resulted in numerous external contributions from features, performance optimizations, and bug fixes. This has resulted in Cutlass being adopted on several major platforms and projects like PyTorch, OneFlow, TVM, Paddle, and over 300 other projects. I'd also like to thank the Cutlass and Qt engineering teams, program management, and compiler teams for their stupendous efforts and contributions in making all this possible. Hopper is a colossally powerful GPU in terms of tensor core throughput, as can be seen by the scaling it provides from 16x for 16-bit types to almost 64x for sparse integer ops. Built on the 4nm process, Hopper contains a rich set of features and is one of the most complex architectural innovations NVIDIA has done over the years. Some of them include a brand new hierarchy in the thread execution model called thread block clusters, which can now share data amongst themselves. A new way to also move data has been provided, which alleviates the burden on SIMD cores significantly. New floating point data types for significantly faster and more energy efficient computation have also been added. Put together, all this make Hopper hit unprecedented petaflop scale performance on a single GPU. The implications of these vast set of innovations in a single architecture means it's fundamentally changed everything from the CUDA programming model to the techniques needed to achieve peak performance on computations like GEMS, which we'll see about in detail. Putting some of those multiples to perspective, The fourth generation tensor cores provide tremendous throughput measured in terms of flops. Also can be seen is that the MMA operations are now of a fundamentally larger shape in Hopper, and we'll see why. We can also see the progress over the years in terms of both speed up entering the petaflop scale and also new formats being introduced and supported. Now, looking at the fundamental MMA operation in Hopper, similar to prior architectures, it implements the op d is equal to op of a comma b plus d. But some of the striking features of the fourth generation tensor cores are that it's warp group wide, where a warp group is a grouping of 4 adjacent warps in a thread block or 128 threads. Second, it's asynchronous in nature, which means it needs to have explicit synchronization operations, kind of like other operations which users are familiar with in prior architectures like copy async. It's capable of loading operands directly from shared memory via descriptors, thus saving on precious register space, which can be repurposed. So the warp group-wide MMA async operation cooperates together, sharing input operands amongst the entire warp group optimally when loading data from shared memory. And they hence also collectively hold the output accumulators. Unlike previous tensor core operations, Hopper also supports a wide variety of MMA instruction shapes in the form 64 by n by k, which helps users to fine-tune kernels for optimal performance, avoiding quantization effects that may happen in certain networks. Here, we can see the sample PTX snippet for a WGMMA MMA async operation, which works on an instruction shape of 64-64-16 with operands being of type F16 and accumulating to a float type. The specification on how data is laid out in shared memory is conveyed through the descriptor object and also transpose operands passed into the WGMMA instruction. There are also options to perform certain kinds of scaling. Hopper also provides a new mechanism to issue asynchronous copies from global memory to shared memory and vice versa, using TMA or Tensor Memory Access. TMA provides a rich set of features which greatly alleviate the burden on the SIMT cores, which was one of the tricky parts of prior generations. Similar to Ampere-era async copies, we avoid a round trip through the register file by directly writing data to shared memory. But some of the other several capabilities built into TMA are that it can multicast data across to other thread blocks in the same cluster and also atomically update async transaction barriers post data loading. It can also perform bounds check on tensor extents and automatically zero fill data for out of bounds data. It can read and write in popular Swizzle data layout formats in shared memory. This is a big benefit. It can also do several other things like handle 1 to 5D tensor coordinates, 2 modes of operation like tiled mode and IM to call, and also supports other modes like reductions and bulk copies. More information can be found on the links attached. Here, we show a graphic illustration of movement of data using TMA. We look at the case where there are 2 thread blocks in a cluster spread across 2 different SMs. And when a warp containing copy bulk async instruction is chosen in one of the SMs, say, it is relayed to the TMA unit which processes this request. It first fetches the descriptor, which in Cutlass is passed by a constant memory, and then converts the copy bulk instruction into appropriate memory subsystem fetch operations. Once the data is ready, it is written directly into shared memory, and at the same time, we update an async transaction barrier with a corresponding number of bytes that have been written into shared memory. Now, depending on the specific copy operations issued, it is possible to also multicast this exact same data loaded to the shared memory of another SM in the same thread block cluster, and also updates its transaction barrier at the same offset. Now, as to who are all the participants in this multicasting operation, it's specified to TMA in the form of a multicast mask. Here we see a sample PTX for a copy bulk async instruction, which is operating on a 2D tensor performing multicasting. As we can see, the inputs are shared memory pointer, the descriptor pointer, and also instructions on how to multicast it via the multicast mask, coordinates, and also the barrier pointer.
Hi, my name is Chris Cheka, and I'm a research scientist at NVIDIA. I founded the Q project while investigating new programming models for tensor computations. Q is a new library that is included with Cutlass 3.0, and it's used as Cutlass's backend to aid in compactly writing speed-of-light dense linear algebra kernels. In this section, I want to give some of the background and motivations for Qt, an introduction of some of its capabilities, and an overview of how Cutlass uses it to make code easier and cuter. First, what is Qt? Qt was born from work with CUDA tensors and principally provides the layout and tensor types. Tensors package everything we need to know about the data we're working with: the type of the elements, the logical shape of the data, the memory space of any storage, and most importantly, the layout of the data. Layout defines a mapping from our logical system to the data indexing, so writers don't need to do the bookkeeping themselves. Importantly, layouts can be hierarchically multidimensional, more on what that means shortly, and shapes and strides can be known at runtime, compile time for efficiency, or both. Furthermore, layouts can be manipulated, combined, split, tiled, composed, which means that Qt can build more complicated layouts from simpler ones, or partition arbitrary layouts of data across arbitrary layouts of threads. Qt is able to synthesize new layouts so that you'll always get the right thing. In Qt, layouts are used for both threads and data, and subsume every Cutlass iterator, of which there are many. That is, all of the custom implemented iterators on the right in Cutlass 2.x, one iterator implemented for every tensor core, every memory ordering, every tiling, and every stage of computation can be replaced with a single layout concept. Rather than performing complicated indexing arithmetic and making sure our iterators agree across code boundaries, Qt layouts manage this bookkeeping for us and provide powerful correctness guarantees. Furthermore, layouts are themselves elements of a formal algebra, which are used to manipulate, combine, and create new layouts more easily. Layouts can be used in functional composition. We can find complements of layouts, inverses of layouts, and use those primitives to build even higher order operations, like concepts of logical products of layouts, logical divisions of layouts that lie at the core of tiling and partitioning, some of the most complicated indexing and bookkeeping intensive challenges in highly parallel environments like CUDA. So let's talk about Qt layouts, how they're defined, and how you can use them. Then I'll introduce some motivating examples behind the algebra to manipulate layouts. With that, we'll have the tools we need to define metadata for every tensor core, from Volta to Ampere to Turing to Hopper. That metadata fully describes the instruction it wraps and allows it to be used much more easily in code. Principally, layouts are simply functions from coordinates to offsets. Here I've shown 4 common layouts: row major, column major, padded, and mixed. Note that the coordinate space doesn't change, while the storage of the data does change in each case. In layout representations, it's common for every shape to have an associated stride, and the map from coordinates to offset is computed via the inner product between the coordinate and the stride. Many libraries, including MD-Span and the C++ standard, take this idea and naturally extend it to arbitrary rank. I'm showing a row major stride, a column major stride, and a rank 3 tensor layout on the bottom. In tensor algebra, a very common operation is to fold a high-rank tensor into a lower-rank object. Here I'm showing a rank 3 tensor with some specific storage, and that same storage viewed as a rank 2 matrix. The tensor has been folded into a matrix, and now we can use matrix algorithms like gem. This particular folding works out nicely. But this particular folding does not work out nicely. There is no integer stride such that the data can be viewed as a matrix in this way. Even though this is a perfectly valid matrix to draw and lay out, it can't be described with a simple 2-dimensional shape and stride. Unfortunately, this is common. We need a more powerful layout representation. Qt solves this by grouping the modes of the tensor into a multi-mode, rather than combining them into a single mode. A hierarchy of shapes is required to represent this view. The offset can still be computed via the inner product of the natural coordinates with the stride, but we need to map our normal coordinates into the tensor's natural coordinates first. That is, each row is assigned a 2-dimensional coordinate, this is the natural coordinate, and to those we assign integer coordinates again. Once we do that, the folded tensor can be treated exactly like a matrix again. With these ideas, we can define the key concepts within Qt. First, the shape is of concept int tuple, an integer or a tuple of int tuples. It's self-referential and recursive. All of these tuples of integers are shapes in Qt. A shape and a stride are combined to form a layout. A layout is principally a map between the coordinate spaces and the index space. Then, a layout and an iterator can be combined to form a tensor. And finally, the primitives of the layout algebra are defined and can be used to manipulate layouts and generate new layouts. Let's revisit the coordinate spaces. A layout is a function object that maps logical coordinate spaces to each other and to storage indices. Every layout has a 1D logical coordinate space, an n-dimensional logical coordinate space, and potentially a hierarchical or natural coordinate space. The inner product of the natural coordinate with the strides produces the storage index on the right. This has some interesting implications. Every tensor is also a vector. It has one-dimensional coordinates. A matrix layout can be way more than row major, column major, padded. It can be interleaved or pitch linear. It can have other tensors inside of it. Some algorithms like GEM will require inputs to have two-dimensional coordinates. Other algorithms like copy will only require inputs to have one-dimensional coordinates. Under the hood, all of these coordinates are mapped to the natural coordinates and then to the storage index. The representational power of Qt layouts is quite broad. As an example, I'm showing a 3-layer Morton-ordered layout function built up from smaller layouts. There are various ways to ask a layout about its shape. This layout has 64 total elements and could be viewed as a vector. It also has 8 by 8 elements and could be used as a matrix. As shown, we can index into this layout like a vector, like a matrix, or like a tensor, using any of the coordinate spaces that this layout admits. Similarly, we can slice into this layout to get sublayouts, and I'm showing subvectors and submatrices here. On this slide, I'm showing additional examples of layouts that appear commonly in CUDA and can be written easily in Qt. On the left, a padded column major layout. In the middle, a pitch linear rank 1 vector layout. And on the right, a column major interleaved layout. In general, it's pretty easy to transcribe these, and it's very easy to create one of your own. In addition, Qt supports swizzle layouts as well, to avoid shared memory bank conflicts, for example. Though writing them takes more practice, and I won't go into the details here. At least they are easy to visualize and toy around with. We've found that being able to experiment with different layouts of data has made the optimization process in CUDA much easier. I've talked about the representations that Qt allows. Now let me introduce some of the motivation behind the algebra and how we use that in CUDA. The algebra itself consists of 4 fundamental operations: concatenation, composition, complement, and inverse. I'm going to focus briefly on composition. Suppose we have a vector that we would like to partition. Specifically, I would like to extract these 6 elements out of this vector. I can list the coordinates of those elements, and my first observation is that those value coordinates can also be described by a layout. What about the other elements? I can fit another set of 6 elements in between the others. And finally, I can fit another 2 sets of 6 after that. Here we have 4 sets of 6 elements in blue, red, green, and gray. I'll call those colors the threads. Each thread wants to receive a different set of the 6 elements. Most importantly, the threads can also be described with a layout. Now we have 2 layouts, the thread layout and the value layout. Combining these, we create the thread value layout, which is a function from thread ID and value ID to a coordinate in the vector. Now we are ready to partition an arbitrary vector using this thread value layout. We take a vector with any layout and perform functional composition with the thread value layout. This results in a layout with the same thread value shape, but the indexing is provided by the layout of the data vector. Then, partitioning is simply taking a slice of the resulting composition. With the thread's index, the red thread now has all 6 elements of the original vector that it is interested in. This is what that looks like in code. We can create an input vector any way we like. We perform a layout composition of that input tensor with the thread value layout. And remember, this is just changing the view of our input data. It doesn't actually cost anything. Then As a final step, we slice the resulting tensor with the thread's index in order to get the partition that we're interested in. The moral of the story is that partitioning is simply functional composition followed by slicing. The thread value layout describes the reorganization of the view to be performed, and the slice actually moves the pointer and changes the layout of that view. And even cooler, remember that I said that every tensor is also a vector. So when I said I'm partitioning a vector here, I'm actually partitioning anything. This might be a 24-element vector, a 6x4 matrix, a 3x2x4 tensor, whatever. Any object that is so-called compatible with a 24-element vector here can be partitioned in exactly the same way. And that's the core principle behind building the MMA atoms in Qt and Cutlass. Every tensor core instruction, MMA instruction, has an associated MMA traits object, which records 3 thread value layouts with it. One for A, one for B, and one for C. Thread value layouts fully describe the instruction and provide the complete metadata associated with it. The thread value layouts can be used to partition any layouts of data according to the pattern. Here I'm showing our first major MMA instruction, the Volta FP16 quad pair instruction, which uses 8 threads with 4 values in A, 4 values in B, and 8 values in C. Similarly, this is an Ampere FP64 8x8x4 instruction, which uses 32 threads, 1 value in A, 1 value in B, and 2 values in C. Again, we can see the MMA traits contains 3 thread value layouts, and it fully describes the metadata of this instruction. These thread value layouts provide the partitioning patterns required by the kernels. This is yet another example, scaling up even larger. The large 16x8x8 Ampere FP16 MMA can be described in exactly the same way. You'll find these MMA traits and MMA atoms throughout Qt and throughout Cutlass. And finally, the new Hopper MMA. Note that, like Pradeep mentioned, the A and B tiles for this MMA aren't actually partitioned, but are instead read directly from shared memory. The shared memory tensors are given to the shared memory descriptor builders that we call fragments, shown here in the element A fragment and element B fragment. These descriptor builders check the input layouts, validate them for the MMA we are about to call, and build so-called descriptors representing the input that already exists in shared memory. The MMA can then consume these descriptors directly. Qt is extremely useful in the Hopper MMAs as well, even though they don't involve partition. And that's because the layouts in shared memory can be inspected by the descriptor builders, checked, validated, and transcribed into these descriptors automatically. And that makes the programming model nearly identical across architectures. There's a lot more to Qt. Today, we've already seen the representational power of Qt layouts and how they generalize on the simple row and column major layouts that we know and love. I've also given an introduction to functional composition between Qt layouts and how we use composition to define arbitrary partitioning patterns and then use those patterns to describe the complete metadata associated with every MMA instruction. There's a lot more to it, in fact. With additional algebraic operations, we can define even higher order operations that look like product and division on layouts, allowing us to build complicated layouts from simpler ones or provide simplified patterns for tiling and partitioning. I recommend reviewing the Qt documentation, asking questions on GitHub, and staying tuned for a more formal white paper description of Qt. Thank you, and I'll hand it back to Pradeep now for more information on what's coming up with Cutlass 3.0.
Hello again. Having had a preview of the Hopper architecture and the Qt programming model, we now continue to see how we have leveraged them in Cutlass. With the upcoming 3.1 release, we plan to add new performance enhancements to our persistent kernels and several other features like register-backed tensor core operations which aid in fusions, and also efficiently pipelined epilogues, and of course the new Python interface for quickly exploring Cutlass kernels. In this chart, we see how important it is to leverage the throughput of the fourth generation tensor cores. On a yearly basis, tensor core throughput has far outpaced Moore's law and remains a critical feature to be taken advantage of by developers. On top of using the tensor cores, if we are able to use lower precision math formats like integer 8 and floating point 8, this brings even more benefits in terms of speedups and energy efficiency. With the help of Hopper tensor cores, we can see that we are almost getting a 19.1x speedup compared to using traditional FP32 SIMT cores. And this growth essentially has led to networks from taking weeks to converge to seconds these days. Now, on to how Cutlass is organized. Folks who have attended prior Cutlass talks in GTC may be familiar with the hierarchical software architecture that Cutlass provides. The abstraction serves as the convenient way to map the CUDA execution model to perform operations like moving data from global memory to shared memory to register space, which are then finally accessed by the tensor cores. Hopper has a slightly different architecture where, while the CUDA execution model has added more levels to the thread execution model hierarchy, it also adds architectural optimizations to remove some of this expensive data motion. For instance, with the help of thread block clusters and bulk copy TMA instructions, we can now move data with minimal back and forth movement across memory hierarchies. And also, the fourth generation tensor cores can now read and reuse tensors directly from shared memory. So accordingly, in Cutlass, we have moved away from a more hardware-centric CUDA execution model-centric hierarchy to a more conceptual hierarchy, aiming to provide interoperability and uniformity. Thus, it allows for flexibility for different architectures to collaborate differently across different levels of the execution model when trying to achieve the same functionality. Thus, it helps keeping a consistent software abstraction layer which remains reusable across different architectures. So if we were to peek into the Cutlass tree hierarchy, it would start off with the device layer, which users are most familiar with and interact with most often when launching a kernel. It contains a handle to the kernel itself and logic necessary to set up the device with things like workspace, shared memories, and also passing along the parameters and launching the kernel itself. Below that is the kernel layer, which embodies all the threads across all the blocks cooperating to perform this gem or convolution operation. And it is also the place where optimizations like swizzling, stream-k, and some of the outer loop schedule management and thread partitioning needed for specialization happens. It's the composition point for back-to-back gems as well. Underneath is the collective layer, which represents the largest group of threads cooperating to perform a particular math or copy operation. These threads also orchestrate some of the outer loops in the gem computation, which are dynamic in nature, and in addition to that, provide synchronization primitives needed to perform the computation. This is the composition point for algorithms, say, which want to fuse operands immediately prior to the main loop or wish to orchestrate the main loop itself slightly differently, like in the case of 3x TF32 kernels. Now, crossing over purely to the Qt side, we have the tile MMA and copy abstractions, which represent the total number of threads collaborating to perform a particular math or copy operation. This abstraction is what we refer to as the microkernel layer, as it helps compose the entire MMA or copy operation that is required by this cooperating group of threads. At the lowest level, we have the atom layer, which is the minimum number of threads which is required to collaborate in order to achieve a very specific instruction or operation. Say, in the case of an Ampere tensor core operation, we need to span an entire warp to perform the tensor core operation. Versus in Hopper, as we saw, we would need to cooperate on an entire warp group level. This is also the level which contains the PTX abstractions. Here we just show a graphical illustration for future reference. This slide shows the corresponding API layer for the hierarchy which we just saw, and as can be seen, Cutlass tree has dramatically reduced the total depth of the hierarchy, which overall leads to a simplified surface area for the API set as a whole. At the device layer, we have the singular gem universal adapter, which is now compatible with both Cutlass 2 and Cutlass 3 kernels. And then at the kernel layer, we have the gem universal, which is tagged based on the appropriate dispatch schedule. The collective layer similarly has a uniform API, which follows the same tagged dispatch policy, just like the collective layer, just that the policy here signifies a main loop schedule to be used, which can be things like a multi-stage or specialized from registers or shared memory, etc. The benefit of building it this way is that users can now freely compose the kernel level and the collective level independent of other things like the microkernels that are needed and the atoms needed to operate underneath. Speaking at the kernel level API, we find the gem universal similar to Cutler's 2.x APIs, and each gem kernel is composed of mainly a main loop and an epilogue. The kernel also includes several other things like block swizzling, grid planning logic, thread partitioning, which is needed for specialization, and is selected via schedule tags. Here we see the example of an SM90 main loop schedule, which can be composed of two different kinds of kernel schedules, which is a kernel TMA warp specialized or a kernel TMA warp specialized persistent. We'll come to what these terms mean shortly. This slide shows the collective main loop API, which is thread block cluster wide, and it too is stack dispatched based on appropriate dispatch policies. It also carries information with it like layouts, data types, and also the atoms required to construct the underlying microkernels. One of the other improvements that Cutlass 3 aims to achieve over Cutlass 2 is the ability to incrementally customize kernels easily. In Cutlass 2, users would typically use pre-baked default gem configurations or vary some specific template parameters, but it may result in incompatibilities. In Cutlass 3, we try to resolve this by providing a convenience interface on top of the collective APIs known as collective builders, which allows the users to customize portions of the kernels or leave them to the builder to choose sensible defaults. And the benefit of this builder is that it adapts other template parameters needed to be passed into the kernel automatically. And if it is not possible, it provides a clear static assert message. Here we show two examples where users can exactly specify the kernel schedule like TMA warp specialized persistent with 5 stages, or just ask the builder to pick the most optimal stage count and schedule for this particular architecture by passing in these auto types. With all our learning so far, the stage is thus set for us to tackle the problem of developing a high-performance matrix multiply kernel. The first and the foremost is the use of TMA for loading data and utilizing thread block clusters to efficiently multicast data amongst thread blocks in the cluster. This saves precious L2 memory bandwidth and also saves the SM from having to do operations like predicate computation and address arithmetic, which used to be pain points. Despite this simplification, it is of critical importance that the TMA issuing threads be kept lightweight as possible, so that they can far outpace the MMA async threads, which are chewing up on the software pipeline. Now, following the async TMA ops are the async MMA ops, of which several need to be kept in flight and synchronized with TMA using transaction barriers, which are hardware accelerated. Here again, keeping the MMA threads lightweight helps in minimizing bubbles in the Tensor Core pipeline. Finally, acting as the glue to hide all of this latency is hardware accelerated instructions for synchronization and the deep software pipelining needed for moving data from global to shared memory. Hopper architecture, with its strong scaled MMA units, requires us to maximize the number of shared memory pipeline stages in order to hit peak flops. A consequence of this is the inability to launch multiple thread blocks in a single SM. What this means is that on top of achieving main loop performance, one also needs to hide the tail and head portions of the gem computation, which we'll cover later via the introduction of persistent schedules. Overall, from this discussion, it may seem quite clear that Hopper brings quite a bit of change to the entire CUDA programming model in the form of separating out the roles of both copying data and utilizing them in the tensor cores via different async threads. This is known as warp specialization. Here we can see that both of these async threads are performing a lot of asynchronous operations in parallel. So it seems paramount to get it both right functionally and also utilize the right set of hardware accelerated instructions for achieving peak performance. The Hopper programming model leans heavily on optimizing asynchronous components, namely the TMA producers and the MMA consumers. With a dozen or more circular buffer shared memory stages, coupled with scheduling logic and the multicasting nature of producers, it remains to have critical software abstractions which aid us in achieving peak performance while also preserving developer sanity. As folks who have worked on distributed systems may know, debugging race conditions in highly multi-threaded and asynchronous environments is not easy. Hence, in Cutlass, we provide a compact set of abstractions which help achieve this producer-consumer synchronization dance happening in Hopper. As seen on the right, we have producer and consumer-specific APIs which greatly simplify this process while also optimally utilizing the underlying hardware-accelerated instructions. We've heard a lot in terms of wording so far, but in order to instill a better sense of understanding on what's going on, we wanted to show pictorially the action inside one of the streaming multiprocessors when running one of these warp specialized kernels. Again, this is meant to be a mere logical representation of things, not physical or hardware accurate. We start off with the specialized producer warps waiting to acquire a shared memory buffer stage, say using the pipeline APIs we just saw. Once they are successful in acquiring, it proceeds to issue the async copy operations to the TMA unit, passing in the right associated parameters with the tensor and also like coordinate information on what to load. When the associated data is returned from global memory, it is written to the appropriate shared memory buffer stage offset, while also atomically updating an async transaction barrier responsible for tracking this exact number of bytes that have been loaded. And this transaction barrier is responsible for tracking not just the bytes loaded by the current load, but also the bytes that it's waiting on from neighboring thread blocks from which it's expecting data to be multicasted. At this time, we may also multicast the data we loaded from this copy instruction to neighboring thread blocks which are waiting on it. Now, moving on to the other side of the story, we have the consumer warps waiting for the barrier to be updated by the copy operation with the appropriate number of bytes needed to fill exactly one stage in the software pipeline. When this happens, the barrier phase flips, which triggers the consumer MMA warps to make progress. Obviously, the next step would be to consume the data which was just produced, and this happens in the form of multiple in-flight async WGMMA instructions, which are capable of reading data directly from shared memory. Once the WGMMA operations complete, which won't be long given the thousands of max per clock throughput, the accumulator operands are written into register memory, and it is time for the consumer threads to release this specific stage of the software pipeline to be filled again by the producer warps. Finally, data is marshaled from registers into shared memory with any epilogue functors that need to be applied prior to this motion. Finally, data is shipped out to global memory using copy async operations. Put together, we see the complete set of operations needed to implement a peak performing gem main loop on Hopper GPUs. Interesting point here to note is almost every single arrow in this slide is carried on by asynchronous operations, and it underpins the importance of good software abstractions to make this both functional and performant. Speaking of software abstractions, this is the entirety of the core collective main loop for both producers and consumer warps in one of Cutlass 3's most efficient main loops, and it fits on a single slide. It also shows the value that Cutlass brings in terms of aiding developer productivity while also handling all this complexity. Moving on, we spoke a lot about how to optimize the main loop, but that alone isn't enough on Hopper. NVIDIA GPUs over the years have scaled up so much in throughput that small inefficiencies come knocking on the doorstep of end-to-end efficiency due to Amdahl's law. Two of them we'll discuss here are the prologue and epilogue operations, which deal with setup prior to the main loop and after the main loop, where we perform element-wise ops and ship to global memory. As hinted before, these operations remain exposed in Hopper when targeting peak flops, and the remedy here is to use what is known as persistent kernel schedules, where we schedule thread blocks to be responsible for multiple output tiles, not just one, and use multiple consumer warps to hide these exposed inefficiencies to maximize tensor core performance. Here, we see the implementation of a persistent kernel schedule, which schedules producer warps to produce data for two consumer warp groups, and the two consumer warp groups ping-pong their MMA execution precisely to ensure maximum tensor core utilization. Also, since these producers and consumers collectively produce multiple output tiles, they amortize the prologue cost across the execution of the entire kernel. Finally, moving on to the last section, in Cutlass 3.1, we plan to release an experimental version of a new high-level interface to Cutlass available via Python. The goals of this high-level Python interface are to make it easy to declare, emit, and compile Cutlass kernels, especially for beginner users, while maintaining the ability to also more carefully tune individual parameters. Another use would be to catch common compilation and runtime errors in Python to ease debugging. Finally, we also plan to make it easy to integrate Cutlass kernels into deep learning frameworks such as PyTorch. As mentioned, the first goal is to make it easy to declare, emit, and compile Cutlass kernels. To achieve this, the Cutlass Python interface provides a high-level operational interface that only requires few template parameters to get started. Whereas one would need to specify many template parameters on the C++ declaration shown on the left, on the Python side, one needs to specify just the data type and layout to get started. But the Cutlass Python interface also tries to retain the flexibility to tune the kernel. For example, if one needed to use a stream K feature, one just needs to set the swizzling functor. And element-wise activation functions are also easy to fuse to the kernel itself. Secondly, the Cutlass Python interface aims to catch common runtime and compilation errors on the Python side that are easy to understand via error messages that are returned. When using the C++ interface, it was common for users to receive long and difficult to parse errors when specifying, say, a kernel configuration that was not supported. On the Cutlass Python side, many such errors, including runtime errors like excessive shared memory usage, can be caught within the Python runtime so that users can receive more descriptive error messages as shown on the right side. Finally, the Cutlass Python interface also aims to make it easy to integrate Cutlass kernels into deep learning frameworks such as PyTorch. The experimental Python interface to be released soon contains a cutlass.emit.pytorch method for automatically emitting a PyTorch CUDA extension for the Cutlass kernel declared via the Python interface. Here we see a Cutlass group gem emit a PyTorch CUDA extension for which under the hood it produces the necessary source files for running the kernel itself and also wrapping the arguments from the input PyTorch data types and also the setup.py needed to install and build the extension. After building and installing, one can directly call the Cutlass kernel within existing PyTorch code. Finally, wrapping up, we released Cutlass 2.11 late last year, which will serve as the last official release of Cutlass 2. Cutlass 3 was released earlier this year, which provides backward compatibility to existing Cutlass 2 kernels, but is our next iteration of Cutlass targeting Hopper tensor cores and beyond. It also brings along with it a new software architecture with Qt as its primary backend engine. Despite its early days, Cutlass seems to be almost on par with cuBLAS in performance. Coming soon, Cutlass 3.1 brings forth a bunch of performance optimizations like pipeline epilogues, fusions, and also the new Pythonic interface, which makes it easy for Cutlass to be accessible to both beginners and also framework developers who wish to quickly experiment with features and kernels available via Cutlass. We also saw in detail about the powerful Qt metaprogramming abstractions and how it provides a coherent and reusable interface which helps Cutlass develop freely composable software layers while providing static consistency checking across a myriad of possible pitfalls. We've started to hear positive feedback from early adopters of Cutlass 3, and our hope is that Cutlass 3 will enable more developer community participation and also innovation. Overall, we'd love to hear more from you on how you'd like NVIDIA and the Cutlass team to help you on your journey. Thank you.